really long because that is only step 2, although I'm taking time to explain it as we go. You won't have to do that when you work these out. Step 3. So now we're going to figure out how does pH, it says what is the pH of 1 liter, same buffer solution, 0.1 molar HF, 0.12 molar NaF. How will the pH, what is the pH when I add 0.02 moles of HNO3? So now we're going to play through a scenario where we add a strong acid, HNO3. This is a strong acid. Remember, you'll have the table of acids and bases and their strengths on the exam, so you could go look at that. So if we're adding a strong acid, let's draw out our little diagram. HA is at equilibrium with A minus. This is our buffer system. How does it respond when we add HNO3? Well, HNO3 is going to dissociate into H plus and NO3 minus because that's what strong acids do. So if we add H plus, remember this is coming from HNO3, the conjugate base is going to see that and say, nuh-uh, I don't want you to mess with pH, so it's going to scoop it up, and together, when they combine, you're making more of your weak acid. So that's how the buffer system will respond. So you can see whenever we add acid, when acid is added to a buffer system, what happens? The concentration of the weak acid, HA, goes up. We make more of it. And the concentration of the conjugate base, A minus, goes down because we're going to use some of it to react with the acid that we add. So keep this in mind as we do our ice chart. All right, now let's do our actual ice chart. So we'll have, here's our ice chart. We're going to have a column for the weak acid, which is HF. We're going to have a column for the conjugate base, which is F minus. Initially, how much do we have? The problem tells us that we have 0.1 molar HF, and we have 0.12 molar of NaF, or F minus, which is the conjugate base. How are these things going to change? Well, they're going to change by the amount of acid we add, and we have to get that in units of molarity. So we're told that we add 0.02 moles of acid and we have 1 liter. Remember, I'm going to come down here. Molarity equals moles of solute over liters of solution. So let's get the molarity of HNO3 so that we can plug it into our column for change. That's going to be equal to 0.02 moles HNO3 divided by 1 liter. So your molarity of HNO3 is equal to 0.02 molar. And thinking about what we just wrote out over here, the concentration of weak acid is going to go up, so I'm going to put a plus sign on that column. The concentration of the conjugate base is going to go down, so I'm going to put a minus sign in the column for the conjugate base. And then you write this value, the molarity of the acid, into these columns. That is how much things will change by. Once you've reacted with all the acid, you won't keep changing anything. I'm going to scoot this minus over. Okay, so now let's calculate our new equilibrium concentrations of the weak acid and conjugate base. We'll have 0.1 plus 0.02 is 0.12 molar, and 0.12 minus 0.02 is 0.10 molar. So these are our new equilibrium concentrations. Now we can plug them in up here in our Henderson-Hasselbalch equation to solve for pH, because that's what the question is. What is pH? pH equals what? pKa. What was our pKa? We plugged it in last time and it still has not changed because we have the same buffer. So 3.46 plus the log, of concentration of A minus, the conjugate base, which is this guy. So our new concentration of conjugate base is 0.1 molar divided by 0.12 molar. The concentration of the weak acid goes on bottom. So now let's plug that in. The log of 0.1 divided by 0.12. And I got negative 0.079. So we have 3.46 minus 0.079. And I got that our new pH will be 3.38. So you see originally, if we go back up to part 1, what was our initial pH? On question number 1, the initial pH of the buffer before we added anything was 3.54. And after we add this amount of acid, we see that the pH drops to 3.38. So our buffer did a pretty good job of maintaining the pH around its original pH. Okay, I'm going to pause this video and